Hi guys, Buildzoid here, and today we're going to be taking a look at a GTX 1070Ti PCB, this time the ASUS STRIX edition. So, this is pretty much the top of the line PCB that ASUS makes for a 1070 Ti. So, let's get right into it. I've decided I'm going to cut out some information and just pile on some others, so ultimately this video is not going to end up shorter. But anyway, you have the three minor rails down here. And for ASUS on ASUS cards, these are you have a 5-volt rail, and the 5-volt rail powers the VRM. It also powers the various voltage controllers around the cards. It provides gate drive for these MOSFETs up here, which technically is the same as powering these, but so gate drive for those, gate drive for those, well, powers that, as well as any other 5-volt logic. I imagine the RGB controller probably runs off of, well, actually, I have no idea. But if there's anything else on the card that runs off of 5 volts, it'll use whichever one of these three is 5 volts. Then there's one for 1.8 volts. 1.8 volts powers some internal PLLs of the GPU core as well as the BIOS. On GDDR5X cards, this would also be fed into the GDDR5X for the VPP rail. However, the 1070 Ti is a GDDR5 card, so, 1.8 volts here is literally just for the BIOS and the PLLs on the GPU core. And then you have your 1 volt PEX voltage, which is also often referred to as PLL, or, I don't like when the L's aren't the same. PEX, PLL, or PCI really depend, I've seen it referred to as that, depending on the card, and ultimately it's always the same voltage. That goes to the GPU core and powers the PCIe interface as well as some internal PLLs. So, and I didn't want that part of the scribbles there. So, those are the various voltages you have around the card. Well, various minor voltages. You don't want to mess with this one. There's no point trying to increase this one or lower this one. It'll just break things. The 1.8 volts generally shouldn't do anything. This one can be helpful on liquid nitrogen. On air cooling or water cooling, it does absolutely nothing. So on LN2, you might want to bump it up a bit. Now then, let's move into the slightly more interesting VRM, the Vcore Vrm right here. This is a 6-phase design. So you have 1, 2, 3, 4, 5, 6 inductors or chokes, whichever you prefer to call them, and for each choke you get 1 power stage. So basically, that there, well, if we include the passive components, then the phase is going to be a little bit of a mess. So we'll just call that a phase, and that makes up 1 phase, and you have 6 of those, so it's a 6-phase VRM. This is controlled by this chip right here, and that chip is a UP9511, which is the standard voltage controller for basically all NVIDIA cards above a GTX 1060. It goes up to 8 phases and up to 600 kilohertz switching frequency. It is completely analog and no I2C interface or any kind of digital data interface. The way this thing does voltage control is there is a PWM signal fed by the GPU to the UP9511, and that is then used to generate a reference voltage, and then the chip aims for that reference voltage. It's very dumb, is basically what I'm getting at. LLC and any kind of switching frequency. Basically, the entire chip is also configured by resistors around the chip, which, if you're into doing a lot of modifications, could be pretty interesting for you. If you're not interested in digging through datasheets trying to figure out how to increase switching frequency or change load line slope, it's kind of irrelevant. But yeah, it is entirely controlled by resistors around it. Here it is running in 6-phase configuration, and I assume 500 kilohertz switching frequency because ASUS have used really high switching frequency capable power stages, which we'll get to right now. So I think it runs on 500 kilohertz. I'm not 100% sure about that. Now then, the actual VRM, the actual power stages making up the VRM, so these chips right here, are Vishay Semiconductor, I'm just going to put the part numbers, SIC 620s. I'm not sure if it's the A variant, but it is a 620 of some kind. And these are 60 amp power stages. So they integrate the driver MOSFET, low side, high side, as well as some logical like protection circuitry. These have OTP, so over temperature protection, which triggers at 160 degrees centigrade. Unfortunately, this will not shut down the VRM. It will merely tell the voltage controller, hey, the VRM is like overheating. You should do something about that. Also, that 160 degrees is internal temperature. So there's like, that's the actual temperature of the silicon inside the package. It is not the, like, if you put a thermal probe, you wouldn't actually see the 160 degrees centigrade temperature when the over temperature protection trips. Other than that, they also offer under voltage protection, and that's it. There's no OCP mentioned anywhere in the datasheet from my reading of it anyway. So yeah, these aren't like super heavily, super heavy on any logical functions. And to be fair, I'm pretty sure the UP9511 doesn't really have support for much more than just temperature protection anyway. So that's, that's not really a huge deal. Now, in terms of actual efficiency figures, these are nice 60 amp power stages. So when it comes to pushing current into the GPU core, you're going to be looking at 5 volts gate drive, so 5 volts drive, because remember we do have that 5 volt VRM on this card, which is used for all the driving. I'm assuming that 500 kilohertz, and normally, under normal operating conditions, you're going to be, well, stock would be like 1.06 volts, and you'd be looking at around 150 amps for the GPU core. At which point this VRM will produce about 8 watts of heat. If you start overclocking it and max out the voltage slider in Afterburner, you'll be at 1.09 volts. Though I've heard apparently the latest Afterburner update goes to up 1.2, but I don't have any NVIDIA cards, so I can't actually check that. Well, I don't have any Pascal cards anyway, so I can't check that. But 1.09 volts, you'd be looking at say 200, maybe even 250 amps. Really depends on like the workload and if you're bouncing off the power limit or not. So at 200 amps, you'd be looking at about 14 watts of MOSFET heat output. So this is just heat output from the MOSFETs. I'm not including inductor losses or capacitor losses in this. At 250 amps, which I think is kind of unrealistic, maybe on 1.2 volts you might actually hit that. But on 1.09, I don't think you're going to hit that. You might go a bit above 200 amps, which is why I'm actually including this to give you a heat output range, so to speak. So at 250A, you'd be looking at about 18 watts of heat output, which is really not bad. This is respectable. There is 1070 Ti's that actually do better at least at the 200. Well, actually, they do better at the 200 amp and the 250 amp rating level. But for a 6-phase VRM, this really isn't anything to complain about. So ultimately, it depends on cost balance, that kind of thing. Though I would like to point out, for those of you interested in like competitive benchmarking, ASUS has been ridiculously consistent. Well, this year they put on 2 overclocking competitions on HW and for me that's actually like a selling point for ASUS cards at this point. Like, it's just knowing that I can buy an ASUS GPU and then use it in a competition. That's a nice little bonus, in my opinion, and it helps that ASUS never really does, like, this VRM isn't so bad that I would consider like trading this. Sure, there's going to be VRMs out there that are better than this. I don't think they'd be that I wouldn't see them as that much of an improvement to actually bother with going for those. Anyway, if you do decide to go competitive overclocking on this unfortunate card, you'll probably max out around 1.35 volts, just because the JP104 chip really doesn't like super high voltages. Like, it just straight up stops. It really doesn't work well at very high voltages. In excess of, 1.4 volts starts being problematic on most cards. And in my experience, I think my 1070 maxed out around 1.35 as well, or 1.38. It never really got up to 1.4. So you're going to hover around lower voltages. I've also heard that, other cards can't even go over 1.3, so it depends on the card you get. But 1.35 volts, you might be looking at current draws as high as, say, 300 amps, at which point this VRM will produce about 30 watts of heat. And that is including the voltage increase. And that's a pretty significant amount of heat. So if you do have the card on liquid nitrogen, also keep in mind this is a GDDR5 card. So, these memory chips right here kind of act as a thermal barrier between any of the cold from the GPU core actually hitting the VRM. So you're going to want to put a high RPM fan over the VRM if you don't, because the heatsink for this card, the VRM heatsink, is part of the actual main heatsink of the card. So there's no base plate that you can keep installed while you have the LN2 pot. So you will need to throw some airflow at this, because 30 watts is not an insignificant amount of heat to try dissipate without an actual heatsink. So, but a 2000, maybe 3000 RPM fan should have no issues dealing with that. So yeah, and you'll probably, I don't think you might not even get to that 300 amp figure. I'm really not sure how much power consumption JP104 hits on liquid nitrogen. I've not seen any testing of that. So yeah, but I assume it's somewhere around 300A, because I had no issues running a GTX 1070 on liquid nitrogen, with quite an anemic VRM to start with, like a lot worse than this. And the GTX 1070 is not that much cut down to be significantly lower power consumption, that much lower power consumption to make a huge difference. So that's the Vcore VRM. Overall, it's not the best 1070 Ti VRM. I've seen better, but it's certainly not disappointing in any way, shape, or form. I think even for liquid nitrogen, it'd be completely adequate. And it can actually deliver, it can deliver full power all the way up to 125 degrees centigrade. And the maximum, external temperature. Internal temperature is maximum 150C, which is why the OTP kicks in at 160. Because 150 would actually be perfectly fine for the internals of the MOSFETs. Now, everything around the MOSFETs will probably complain, especially all the, aluminum polymer capacitors around here. These are FP series Nichicons. These are 5K. These aren't 5K. That's interesting. But, so these are, FP series 5... No, actually, no, these aren't FP series. These are... I forgot the manufacturer. These are Nichicons. These are Japanese. But these are a Taiwanese manufacturer. I can't remember the name right now. They're really, what was the same capacitor manufacturer as the Gigabyte Gaming K5. Either way, these are still 5,000 hours rated at 105 degrees centigrade. So, it's kind of bog standard aluminum polymer capacitor rating. These days, well, normally you get 2,000 or 2,500 hours rated capacitors, but better manufacturers like ASUS and MSI and Gigabyte pretty much always use 5,000 hours anyway, so for custom cards I kind of expect 5,000 hours to be the bare minimum, really. For reference models, 2,000 hours is the usual selection. Either way, I don't think capacitors will have an issue here on normal operation, and on liquid nitrogen you're not going to run the card that long to actually have to worry about that rating anyway, because it's for thousands of hours, and that would cost a lot of money to do with liquid nitrogen. So yeah, that's all very well and good. Now let's move on to the memory VRM. This is a single phase. Powers all of the GDDR5, so it pushes 1.5 volts to that. And quite frankly, I'd prefer seeing a two-phase memory VRM design, just because one phase is I'd like to do more testing on this, but with my 1070, for example, which was a single phase card, I did notice that it helped, I did have an improvement from adding extra capacitors to the memory VRM, which basically indicates that there was a lot of low frequency noise, and the number one source of low frequency noise is the VRM itself. And typically the less phases you have, the you know, the more 100 like 300 to 600 kilohertz, you know, frequency noise you get in the VRM output, because that's the switching frequency of the VRM. So that goes basically straight to the voltage output. And really having a two-phase would improve that significantly. For that reason, for the actual single-phase memory VRM up here, which is controlled by this chip right here, which is a UP1666, the drive voltage is still 5 volts, just because the UP1666 runs on that. This is a two-phase controller, but as you can clearly see, ASUS is running it in one phase, and the other thing is it goes from like 200 to 800 kilohertz. So I have no idea what switching frequency ASUS is actually running it on. I assume it's probably 300 kilohertz, but on the off chance that it's 600, for 20 amps at 300 kilohertz, and I'm running out of space here as usual. So 300 kilohertz, you know, 20 amps, you'd be looking at, say, because, oh right, I forgot to mention the MOSFETs. These are your typical cheapo onsemi 4C09N, and that is a 4C06N. Low cost, low side FET, and high side FET of choice for ASUS recently. They've used these on a bunch of motherboards, so I'm not really surprised to see these on GPUs. You do get two high sides and two low side FETs, so they did put at least two of them, because actually, if there was only one of each of these, this VRM would end up pretty damn hot. So it's a good thing that they put two of each, but yeah, these aren't exactly spectacular MOSFETs. Anyway, for 20 amps output at 1.5 volts, and 300 kilohertz switching frequency, you're looking at about 3.5 watts of heat output, which is fine. That's in line with most other memory VRMs. Now, if ASUS decided to run it on 600 kilohertz, that same current throughput would give you 5.6 watts of heat output. That's a bit high for a memory VRM. So I don't think they're actually running it off of 600 kilohertz. In which case, you know, I imagine it might be pretty noisy, because it has, like, my 1070 was apparently pretty noisy. So yeah, because it's a single phase at 300 kilohertz. Other specs on the UP1666, basically the UP1666, since it's on an NVIDIA card, has the same control capabilities as the UP9511, so PWM signal goes into the chip, and that is used to generate the memory voltage. Not much else to it. Similarly, all the actual settings on the chip are configured with resistors around it, and there's no software monitoring for it. So that covers this side of the card, and that took incredibly... Actually, no, it doesn't. Here's your current shunts. And you know what? Since this channel doesn't cater to casuals anyway, these are, you know, these are your current sensing shunts. You short them out. Figure out how to do that yourself. I mentioned it 1,000 times before. No. Well, I can't be bothered. This is taking too long. Let's go to the back of the card. But those are the shunts you'd want to short out for your extra power mod. Back of the card is very boring, mostly. We do have voltage modification points up here. I assume that in order to enable them, you have to short this pad right here, but don't take my word for it, because this is not labeled at all. So, yeah, I'm not entirely sure about how that is set up, which is kind of unfortunate. Other than that, the current monitoring chip, the INA3221, that is standard for all NVIDIA cards, is right here. And basically, if you want to blow out the power limit the hardcore way, there's ways to make this chip read a fixed amount of power consumption, so that the NVIDIA driver completely gives up on trying to do anything to your core clocks, which is kind of cool, but also really finicky, because you have to remove a few resistors and then add a bunch of new ones in order to get the voltage ratios right. But yeah, that is definitely an option if you're interested in that, because I've done that on my 1070, and there is a video about doing that on the YouTube channel. Moving on, you also get voltage read points, which is kind of cool if you're trying to like debug the card and you're not sure where everything is. So you have vGPU, vMem, 1.8 volts, vPEX. I have no idea why both of those are right here when the VRMs for like all three of the minor rails. Also, here's 5 volts, right? So all the minor rails are in this area, and then you get like 2 of the read points are here. One of the read points is there. It just doesn't make any sense to me why they laid it out like this. But hey, at least you have read points that are easy to find. That's a lot better than some cards where you have to probe around. Well, you'd probably just end up probing from the inductor output to a capacitor that you find that reads 0 ohms, and that would probably be your probe point because there's not really a better way to find a good probe point if they're not labeled for you like this. You also have 3.3 volts. This should never be missing. If this one is missing, you have a problem here. Speaking of which, that should also never be missing. 12 volts and 3.3 volts come from the PCIe slot. If these are reading 0, there's something very, very wrong with the system. And then you have a ground point, which this one I don't get. Like, this one seems really redundant. It might be for ASUS's manufacturing line because, like, that's a ground, that's a ground, that's a ground, that's a ground, that's a ground. I think at this point you get the idea. That's a ground. That, surprisingly, is not a ground. That's Vcore. That there is. I assume this, like, I've seen this on a few ASUS cards. I'm actually not sure what it's for. Like, ASUS had one card in the past where they had a copper tab that went from something like this, and then right behind the GPU core. And basically it was like a power bridge thing, which, I mean, it makes sense. Like, more copper in the power plane is always more better, but I'm not sure if it's a relic of that, or, like, why this exists at all, because it's not a mounting point. It might be for the factory, maybe? I don't know. It seems really... because no other cards have this. I have no idea why that's a thing, but it's a thing. I still think it's probably for the power bridge. Because, yeah, you can see it's hooked straight into Vcore. So it's not even grounded. Yeah, that's a... I assume it's for a power bridge that they just decided, nah, it's too much marketing, it costs too much to do, or it's not worth doing in the first place. I'm pretty sure I covered everything at this point, haven't I? Oh, and you get some LEDs to indicate if the 8-pin is plugged in or not. So, yeah, that's the card. It's pretty, like, it's pretty standard ASUS STRIX, really. You get a good, strong VRM. It's not the world's most ridiculous 1070Ti PCB ever, but, you know, it's not a PCB I would complain about. You get your standard 5,000 hours rated capacitors from Taiwan. And I dropped my pen. What else is there? Yeah, your current shunts are here, and give me a second. Like, let's just go over the current shunts since I do feel like I have a bit of extra time. Yeah, we're at 22 minutes. That gives me overtime. So, you'd only want, on this card, you'd only want to short these two because all of your power for the Vcore Vrm comes through this 8-pin. All of that power is measured by these two shunts. And then it basically, well, somehow it gets from this part of the board to this part of the board. It's a multi-layer PCB. I can't see the freaking layout. And then it goes into your Vcore Vrm, and your Vcore Vrm is literally hooked into just the 8-pin. The PCIe slot down here basically powers the memory. Yeah, the memory VRM. Probably these guys down here, as well as the fan. Actually, no, this one right here. No, this one's... actually, I'm not sure about this one. No idea about this one. This one might be powered off of the 8-pin as well. But the PCIe slot would also power the GPU core fan headers, which I assume are these. Because I can't see anything else that looks like fan headers on here. Cool. Okay. Well, one of those is the fan header. The other one is the RGB port. And then you get 2 more fan headers on here. I don't know how those work. I've never used it. Well, I had an ASUS card. I never used these. And I think I'll wrap it up there. Even though I feel like pointing out that it looks like that this might have once... there might have once been plans for dual BIOS on this card. Because that sure looks like an extra BIOS mount. And that sure looks like a switch mount. So, yeah, that's it for this PCB breakdown. It's a STRIX card, you know? I don't feel Well, if you go far down enough in the price, you know, into like the low end GPU category, you start seeing Strix cards where you can't say, okay, well, I don't know. I don't feel like I've seen a Strix card where I'd say the VRM is outright terrible. I've seen some where I would say the VRM is not good, but this one's definitely one of the good ones. You know, it's a strong 6-phase, and a 1070 Ti really doesn't need more. Even on liquid nitrogen, it doesn't need more. Other than that, it's kind of run-of-the-mill NVIDIA cards. It's nice that the back of the card has all those voltage read points. I personally appreciate that quite a bit, because it does make things a lot simpler when you want to get voltage readings. Anyway, that's it for this video. Thank you for watching. Like, share, subscribe, leave a comment or complaints or questions down below. If you would like to support what I do here with actually hardcore overclocking, I have a PayPal, a Patreon, and there's shirts. You can find all of those down in the description below. They're all under one link. Don't go looking for like separate Patreon links. They're all one link because, well, it makes the description less massive. But, what else was there? One last thing I wanted to mention. Right. Thank you to techpowerup.com for taking such nice high-resolution PCB pictures, because without them, a lot of these cards wouldn't be possible. Well, a lot of these PCB breakdowns wouldn't be possible. And that's it. So, thanks for watching one more time, and goodbye. I can't find the stop button.